we're going to continue some weak acid type of problems. Remember, weak acids only donate some of their hydrogen ions. Okay, that's the difference between weak and strong. So if it's strong, take the negative log of the concentration, done, pH. If it's weak, it's a little more complicated. Now, in this problem, we're going to determine the Ka of the acid. And we're given a couple things. We're given the concentration of the solution, hydrocyanic acid, hydrocyanide, ide, changed to ic, hydrocyanic acid, and it has a pH of 5.0. It probably looks like 5.0, okay? All right, so I think the habit you should get into, let's use the Brownson-Lowry model and write the reaction. HCN, solution of HCN with H2O liquid is in equilibrium. Remember, double arrows, so these reactions are reversible. So of course we know this donates a hydrogen ion to this. We'll get hydronium ions in solution. And then we'll get, look at this. So this loses an H plus 1. Lose something positive, it's going to become negative cyanide ion. That's the conjugate base of that acid. Okay, let's use the ICE table. ICE. Initial change, equilibrium. So, let's see. Do we have to do this in this situation? Yeah. So let's say this is 0.20. We don't care about the water because it's not in the expression. We don't have any of this. We don't have any of this. The change is going to be minus x. Some of this is going to dissociate. Plus x, and that equilibrium will have this, okay? All right, next step, let's write the expression. So Ka equals the concentration of hydronium ions times the concentration of cyanide ions over the concentration of HCN, all right? Okay. So what's X in this case? Yeah, so X is equal to the concentration of hydronium ions, right? And that's also equal to the concentration of cyanide ions, isn't it? Because for every one of these, we get one of these. Now, what do we know? How can we incorporate knowing the pH of this solution? Think about what that's equal to. This is also equal to 10 to the negative pH, right? So we're trying to figure this out. So we need to know all this stuff. I mean, this is what we're trying to find. So Ka equals, so we know what that is. It's 10 to the negative 5.0. That's the pH, right? This is the same as this. These are the same. These are equal. These are equal. 1-to-1 ratio. 10 to the negative 5.0. Divided by, all right, then this is this, 0.20 minus an x, of course we said was this, 10 to the negative 5.0. All right, so let's do that on our calculator and see what we get here. 10 to the negative, of course we know what this is. Let's not do, we know this is 10 to the negative 10th, right? So you add exponents when you multiply. So we should do this on our calculator though. So it's 2 minus, this is 1.99999. So let's divide those, okay? So Ka is equal to 5.0 times 10 to the negative 11th. And I think, let me check my notes here for a second. Sorry about that. Hey, I think I might be off a decimal place here. Let's just check again. One point minus. No, that's right. Oh, no, it's this. My fault. Yeah. Check it yourself. Make sure you get 5.0 times 10 to the negative 10th. Okay, sorry about that. That's the Ka. All right. Hey, okay, so this is we're given pH, given concentration, initial concentration of the acid, determine Ka. We wrote the equation, Brownson-Lowry model, expression. This is kind of like, this isn't new, but yeah, this is new. Knowing this, taking advantage of this is new. So that's that. All right, you know what? Let me do one more thing now. Let me show you how to figure out the percent ionized. So the percent ionization. Okay, so that's going to be the concentration of hydronium ions right here. 1 times 10 to the negative 10th, to the 5th, excuse me, divided by the original concentration of the acid, 0.20, times 100. So you might be asked to figure out the percentage of the percentage of these acid molecules that are ionized, meaning the percentage that lose their hydrogen ions, okay? So this is how we would do that. And so let me just use my calculator again, part of my reach. So 1 exponent negative 5 divided by 0.2 equals times 100. It's so it's a really low percentage, 0.005%, okay? All right. So, thankfully, a little shorter video, right? We're trying to figure out Ka in this case. Now, we'll do the same thing with strong bases and weak bases, okay? And I think you'll see the similarities. Once we do, I'll try to separate this into a couple assignments. Once you have this, I think the weak bases will be easy for you, okay? All right, that's it.